Hello everyone. In this series of videos, we'll be talking about clock tree synthesis. So the word clock by itself tells us a lot of things. In our day-to-day life, we use the clock to plan our day-to-day activities. Similarly, the clock is used on a chip to plan various functionality of the chip. So for example, when we say clock tree synthesis, it actually means the following. So we have this complete chip, we have a square chip. Usually when you open up a mobile phone or any device, you see a square shaped chip. It could be a rectangle also, but let us generalize the things and keep a square shaped chip over here. So on this chip you have this clock endpoints. All these white spots that you see, these are nothing but your flops, your flip-flops, the clock pins of the flip-flops. All these white spots are the flip-flops of your are the clock pins of the flip-flops, and these clock pins are spreaded around the complete chip. The count that I have shown over here are very handful. On a real chip you will have like millions of flops. So this particular so the job of the clock tree synthesis is to take this particular clock who has got this entry point at the bottom of the chip and supply this particular clock to each and every clock endpoint, and it should not be a random supply. So one can say that we can just take this clock signal and route it to this clock pin in this fashion. We can take this clock signal and route it to this particular let's say clock pin in some right angle fashion. So these are all what the questions that will be coming out. And so there are different techniques of building a clock tree. So it is not a preferable way to directly connect this clock pin to this particular clock endpoint. There are certain parameters, there are certain qualities that this clock tree has to pass. It has to retain to those qualities. So in this series of videos, we'll be learning about techniques and the quality check parameters that is used to qualify the clock tree that we have built on a chip. So clock tree, it's a very important thing on a chip, because without the clock, the chip can't function. Basically, it's a pulse that you are going to send to the chip for it to function correctly. And the clock, if not built correctly, it might lead to sleepless nights towards the end, whenever there is a deadline or whenever there is a chip tape out. Keeping all those things into consideration, we have come up with a set of videos which will talk more about the quality checks, which will talk more about the things that you need to take care before even entering into building a clock tree for any kind of chip. So we'll be talking about those things more. We will be emphasizing on the concepts behind the clock tree, and those things will be taken care, and those things, if taken care in the very beginning of the clock tree, it will help us to build a tree with the expected parameters, with the expected quality, and that might not result into a sleepless nights that we usually face during the tape out. So basically, if you build, the clock is the base of your chip. If you build the clock tree better, a lot of your problems get solved if you build a better clock tree. And basically, if a clock tree that is built passes the quality check parameters, which we'll be talking about in this set of videos. So this set of videos will be all about clocks and all about clock and clock trees. So with the help of this particular topic, we have also tried to touch each and every corner of the VLSI. For example, it will also talk about MOSFETs. It will also talk about PMOS, NMOS, and a CMOS inverter, because we have to consider the power. And for learning the power, for knowing how to save power, we have to understand what is this. What is, first of all, what are the different kinds of power, and how is it related to an inverter? If you take a small inverter, what all the power that are coming out of that inverter? We need to understand that part also. So this was a fairly decent topic to touch all those aspects of VLSI, right from MOSFETs to a bigger chip. So that's why we have chosen this topic as an introduction video to the VLSI chip design. So let's start. Let us try to see what all topics we will be covering in this set of videos. So we'll be starting with defining the quality check parameters: skew, power, latency, pulse width, and all those things. There will be a set of quality check parameters that we will be talking about. In the initial videos, we'll be learning about what this quality check parameters are, basically the terms and terminologies with respect to all these quality check parameters. And second, we will be trying to understand what are all these checks. So what do you mean by power, what do you mean by latency, and techniques of how to control it. So we'll be looking into all those in this series of videos. Next, we'll be looking into a basic clock tree with a 16 clock endpoint. There will be a chip which has got only 16 clock endpoints, and we'll be trying to build a very simple tree for this a very simple tree. So in that case, what will happen? We'll be able to understand some advanced concepts while we build this simple clock tree. So we'll be looking into building a H tree with 16 clock endpoints. It's a very basic algorithm for building a clock tree. Next, we'll be qualifying the H tree that we have built against the parameters against the CTS quality check parameters which we looked in the first initial set of videos. So this H tree will be qualified against skew, power, latency, and see and could be and would be seen that what better could be done, or what better could have been done to get a better H tree. So we will be looking into all those, and there will be some problems that we have identified, that we will be identifying from the quality check of the H tree itself, and that will help us to come up with a technique called as clock tree buffering. So in this we will be taking an analytical approach rather than a discussion. We'll be taking a proper analytical approach with equations, where we'll be finding out exact point where we have to place the buffers, and that will result into best skew, best slew, and the lowest power. So we'll be trying to cover that part over here, in this section, where we will be talking about clock tree buffering techniques. And then by using the clock tree buffering technique, we will apply this technique on an H tree and come up with a buffered H tree, and do all the set of quality check parameters that we did over here, and try to find out now what part is remaining out of the quality check that we missed over here. So we'll see the impact of clock tree buffering on a buffered H tree, and then see how the quality check parameters becomes even better when we do a buffered H tree. We'll be looking into that. Next, so this particular H tree will be a simple H tree with 16 clock endpoints, which has got a very regular and even spread. So we'll be looking into a technique where we place the flops randomly on a chip and try to build a tree out of it. So the concepts of the H tree will be still holding good for building a tree for this set of flops, but there will be some additional things that we need to take care of while building a tree for uneven spread of flops. So based on the concepts that we have learned from this five initial points, this will all be applied while building that H tree for uneven spread of flops. So that is quite interesting topic. So we will be looking into that as well. Next, after learning the H tree for a 16 clock endpoints which is evenly spread, and learning how to build an H tree for uneven spread of flops, we'll be moving into an advanced topic where we have to build a tree for millions of flops, because recent VLSI trends, it has got thousands and millions of flops on a chip, and we have to build a tree for the complete tree. So it will be basically building a tree for sub trees. So we will be dividing the complete chip into small sections and trying to build a tree for those sections. So we'll be looking into how to do all that in this advanced H tree for millions of flops. Next, once we are done with the advanced H tree for millions of flops, we'll be looking into some details of how to save the power. So that is the first, because on a chip, if you see, the clock tree is consuming around 70 to 75% of the power. So we have to find out ways and techniques, how do we save power in the clock itself, because there will be some technique to save the power, and that will save power, let's say around 50%, 60% power could be saved. So clock gating technique is a very good technique and a very interesting technique, where we see how can we save power, and also while reducing the power in the clock tree, we also try to maintain the same skew, same latency, and all those things. We will look into all those things in this section, where we talk about clock gating techniques and power aware CTS. And finally, we'll be doing a small static timing analysis. So this section we have included just to understand the impact of clock tree on setup and hold timing. So that is a very important part, because unless and until we apply the clock tree on a real circuit, that it won't be that interesting. So we'll be taking the clock tree that we have built, and doing a static timing analysis to understand the impact of the clock tree, and to understand how, let's say for example, we will try to understand how how a non-zero skew clock tree can impact your setup time, or can impact your hold time. We'll look into all that in the static timing analysis with clock tree. So this won't be a brief section. It won't be the complete discussion on static timing analysis. It will be a brief section where we'll be talking about delay tables and basic hold and timing checks, which with the clock tree applied. So if you tune the clock tree by even a single buffer or by two buffers, how does it directly impact your static timing programming analysis, how does it directly impact your whole time, your setup time. So we'll be looking into all this in this section, and this is a very interesting section, which that's why we have kept it at the end, because this needs the concepts of whatever we are learning over here. That's why this part is kept at the end. So what we'll do is, since I'm already running out of time, from the next video we'll be starting with the CTS quality check parameters. Basically we'll be looking into few quality checks, their definitions, the terms and terminologies associated with those particular quality check parameters. So let us try to look into let us try to start with the quality check parameters from the next video. Thank you.